Welcome! In this session, we will dive into LeetCode problem number 1400, construct k palindrome strings. This problem challenges us to determine if it's possible to construct exactly k palindrome strings using a given string's characters. We'll explore the problem requirements, break it down step by step, and discuss the most effective solution strategies. Let's get started. In this problem, you are given a string s and an integer k. The task is to determine whether it's possible to construct exactly k palindrome strings using the characters of s. First, let's clarify what a palindrome is. A palindrome is a string that reads the same forwards and backwards, for example, radar or level. You can rearrange the characters of s to form these palindrome strings, but there are a couple of constraints. Each character can only appear in one palindrome, meaning that characters cannot be duplicated across palindromes. Additionally, the total number of palindromes must be exactly k. The input consists of the string s, whose length is between 1 and 10 to the power of 5, and an integer k, which also ranges between 1 and 10 to the power of 5. The output is a Boolean value, true if it's possible to construct k palindromes, and false otherwise. Let's look at an example to better understand the problem. Suppose the input string s is Annabelle and k is 2. The output in this case is true. Why? Because we can rearrange the characters of Annabelle to form two palindrome strings, such as Anna and Elle. Both of these are valid palindromes, and we successfully created exactly two of them. Now consider another example where s is LeetCode and k is 3. In this case, the output is false. The reason is that it's not possible to divide the characters of LeetCode into 3 palindrome strings. There are too many unique letters in the string to be able to form 3 separate palindromes. This highlights an important observation: the number of unique characters with odd frequencies in the string plays a crucial role in determining whether we can form the required number of palindromes. Now, let's examine one more example where s is true and k is 4. Here, the output is true. This is because we can form 4 palindromes by using each character of the string as a single character palindrome. Specifically, we can construct T, R, U, and E, which are all valid palindromes. To summarize, there are 2 key considerations when solving this problem. First, to form a palindrome, at most one character in the string can have an odd frequency. Second, the number of palindromes we can form depends on how many characters have odd frequencies. Additionally, k cannot exceed the length of the string, because each palindrome must contain at least one character. Keeping these constraints in mind will guide us toward an efficient solution for this problem. To tackle the problem of constructing exactly k palindrome strings from a given string s, we explored several approaches. One initial idea was the brute force method, which involves generating all possible partitions of the string into k parts and then checking if each partition forms a palindrome. While this approach is conceptually straightforward, it quickly becomes computationally infeasible due to the exponential growth in the number of partitions as the string length increases. For example, if the string length is 10,000, the number of potential partitions to evaluate is astronomically high, making this method impractical for real-world use. Instead, we can take a more refined approach by analyzing the frequency of characters in the string. A critical observation here is that a string can form a palindrome if at most one character has an odd frequency. For instance, the string ab can form abba, as all characters occur an even number of times, while ab can form ababa, as it has only one character with an odd frequency. This leads to the realization that to construct exactly k palindromes, the string must meet 2 conditions: it must have at least k characters, and it can have at most k odd frequency characters, as each odd frequency character will serve as the center of one palindrome. This insight forms the basis for a more optimized solution. Building on this key observation, we can simplify the problem by checking a few straightforward criteria. First, we count the number of odd frequency characters in the string. Then, we determine whether k falls within the range defined by the number of odd frequencies and the total length of the string. Specifically, k must be greater than or equal to the number of odd frequencies, as each odd frequency corresponds to a necessary palindrome center, and it must also be less than or equal to the total number of characters, since it is impossible to create more palindromes than there are characters available. The algorithm to implement this is efficient. First, calculate the frequency of each character in the string, then count how many of these frequencies are odd. Finally, check if the conditions number_odd less than or equal to k less than or equal to lens are satisfied. If they are, return true, otherwise, return false. The computational complexity of this approach is O(n), where n is the length of the string, because the frequency counting and odd frequency checks each require only a single pass through the string. Additionally, while an alternative greedy method could be used to explicitly construct the palindromes, assigning odd frequency characters first and then distributing even frequency characters, this is unnecessary for simply determining feasibility, as the frequency-based check already provides the answer in a more straightforward manner. Given the available options, we chose the frequency count and observation approach as the most effective strategy. This approach directly addresses the feasibility question without requiring the explicit construction of the palindromes, which keeps the solution clean and efficient. Its simplicity lies in leveraging the insight that the number of odd frequency characters and the length of the string are the key factors in determining whether constructing k palindromes is possible. With a linear time complexity of O(n), this method is well suited for handling large inputs while avoiding the inefficiencies of brute force and the complexities of a greedy construction approach. By focusing on the core requirements, limiting odd frequencies and ensuring that k does not exceed the string length, this strategy delivers an optimal balance of clarity, performance, and correctness, making it the ideal choice for solving this problem. To solve this problem, we need to determine if it's possible to create exactly k palindrome strings from the given string s. A palindrome is a string that reads the same forward and backward, and the challenge is to decide if we can distribute the characters of s into k such palindromes. The first step in our approach is to count the frequency of each character in S. This helps us identify how many characters have odd frequencies, which is crucial because a palindrome can have at most one character with an odd frequency. For instance, in the palindrome racecar, the character E appears an odd number of times. If there are more odd frequency characters than the number of palindromes k we want to create, it's impossible to achieve the goal because each palindrome can only accommodate one odd frequency character. Finally, we check the feasibility of constructing k palindromes by analyzing the relationship between k, the odd frequency counts, and the total length of the string. The range of possible values for k is critical to solving this problem. Specifically, k must lie within the range of max, 1, odd_counts, and lens. The lower bound, odd_counts, represents the minimum number of palindromes required to accommodate all the characters with odd frequencies, as each odd frequency character necessitates its own palindrome. The upper bound, lens, ensures that we aren't attempting to create more palindromes than the total number of characters available. If k is smaller than odd_counts or larger than lens, then it's impossible to construct the required palindromes, and we return false. Otherwise, we return true. The key insights here are that odd frequency characters dictate the feasibility of the solution, and the value of k must balance between these constraints. By efficiently counting character frequencies and performing simple comparisons, we can determine the result with optimal time complexity. This algorithm operates with a time complexity of O(n), where n is the length of the string s. This efficiency is achieved by performing a single pass through the string to count character frequencies and a few constant time checks for feasibility. Space complexity is O(a), where is the size of the character set, but since this is constant for lowercase English letters, it simplifies to O(1). To implement this, we use a counter or hash map to store the frequency of each character, and two integer variables to track the count of odd frequency characters and the total string length. This setup allows us to handle edge cases effectively, such as an empty string, a single character string, or strings where all characters are the same. For example, if S is empty, we can only form palindromes if k is 0. Similarly, if S has a single character, forming one palindrome is possible, but forming more than one is not. These considerations ensure the algorithm accounts for all possible scenarios. Another important edge case occurs when the number of odd frequency characters exceeds k. For instance, if the string s is ABC and k equals 2, it's impossible to distribute the three odd frequency characters into just two palindromes, so the answer is false. On the other hand, if k equals the length of the string, each character can form its own palindrome, making the answer true. The algorithm is designed to handle such scenarios efficiently. In terms of complexity, counting character frequencies is O(n), since we iterate through the string once, and our comparisons are constant time operations. The space complexity remains O1 for the fixed-size character set. These properties make the solution scalable and suitable for larger input sizes. By focusing on the distribution of odd-frequency characters and the feasible range of k, we ensure the algorithm is both correct and optimal. The Python implementation of the algorithm begins by counting the frequency of each character in the string using the counter class. Next, we count how many characters have odd frequencies. This is done with a simple generator expression that iterates over the frequency values and checks if each value is odd. Once we have the count of odd frequency characters, we check if k falls within the valid range. Specifically, if k is less than the number of odd frequency characters or greater than the total length of the string, we return false. Otherwise, we return true, as it's possible to construct the required number of palindromes. This concise implementation highlights the efficiency of the approach, leveraging the character frequency count and a few key logical checks to arrive at the result in linear time. To illustrate the algorithm, let's walk through two examples. In the first example, where S is Annabelle and k is 2, the frequency count shows that only one character, B, has an odd frequency. Since k is within the valid range and greater than or equal to the odd frequency count, the answer is true. In the second example, where S is ABC and k is 2, all three characters have odd frequencies. Since k is less than the number of odd frequency characters, the answer is false. These examples demonstrate how the algorithm efficiently evaluates the feasibility of constructing k palindromes by focusing on the distribution of odd frequency characters and the constraints on k. To solve the problem of determining if it's possible to construct exactly k palindrome strings from the given string S, we use the following approach. 1. Initial check asterisk if k is greater than the length of the string S, it is impossible to construct k palindrome strings because we would not have enough characters. Therefore, we immediately return false in such cases. 2. Character frequency count asterisk using Python's collections counter, we calculate the frequency of each character in the string S. This gives us a dictionary where the keys are characters, and the values are their respective counts. This step allows us to determine how many characters have odd frequencies. 3. Odd frequency count asterisk for a string to be a palindrome, at most one character can have an odd frequency, this character would occupy the center of the palindrome. To construct k palindromes, the number of characters with odd frequencies must be less than or equal to k. We calculate the total number of odd frequencies using a generator expression that iterates over the frequency values and counts how many are odd, count %2 equals 0. For final decision asterisk if the count of odd frequency characters is less than or equal to k, it is possible to distribute the characters into k palindromes. Otherwise, it is not. The result is returned as a Boolean value. This solution is efficient with a time complexity of O(n), where n is the length of the string, as we only iterate over the string once to calculate frequencies and once to count odd frequencies. The space complexity is O(1) for the frequency dictionary since it contains at most 26 entries, one for each lowercase English letter. This is the Java implementation of the LeetCode problem number 1400, construct k palindrome strings. The logic mirrors the Python solution, where we first check if k exceeds the string length, impossible to form k palindromes. Next, we use a hash map to count character frequencies and calculate how many characters have odd frequencies. A string can be split into k palindromes if and only if the number of odd frequency characters is less than or equal to k. Java-specific syntax includes explicit type declarations and the use of the hash map class for counting character frequencies. To solve this problem, we start with the string S equals Annabelle and need to determine if it's possible to construct two palindrome strings. The first step is to check whether k, the number of palindromes we want to construct, is greater than the length of the string. Here, the length of S is 9, and k is 2. Since k is not greater than the length of the string, we move forward. Next, we count the frequency of each character in the string using the counter function. This gives us the result, a 2, n, 2, b, 1, e, 2, l, 2. From here, we identify characters with odd frequencies, as these will determine the number of odd-length palindromes we can form. Only the character b appears an odd number of times, so our odd underscore count is 1. Finally, we compare odd underscore count with k. Since odd underscore count is 1 and k is 2, and because odd underscore count is less than or equal to k, we determine that it is indeed possible to construct two palindrome strings. Therefore, the output is true. Now, let's consider the string s equals LeetCode with k equals 3. As before, we begin by checking if k is greater than the length of s. The length of s is 8, and k is 3, so we proceed to the next step. Using the counter function, we calculate the frequency of each character in s, which gives us L1, E3, T1, C1, O1, D1. Next, we count the characters that have odd frequencies. In this case, the characters L, T, C, O, and D all appear an odd number of times, resulting in an odd underscore count of 5. Comparing odd underscore count with k, we find that odd underscore count is 5 and k is 3. Since odd underscore count is greater than k, it is not possible to construct 3 palindrome strings. Therefore, the output is false. Finally, consider the string s equals AAA with k equals 3. As usual, the first step is to check if k is greater than the length of s. Here, the length of s is 3, and k is also 3. Since k is not greater than the length of the string, we continue. Using the counter function, we calculate the frequency of each character in the string, which results in 3. We then count the characters with odd frequencies. In this case, only the character A has an odd frequency, so the odd underscore count is 1. Comparing odd underscore count with k, we see that odd underscore count is 1 and k is 3. Since odd underscore count is less than or equal to k, we conclude that it is possible to construct 3 palindrome strings. Therefore, the output is true. Here, we analyze the time complexity of the canConstruct function. First, we count the frequency of each character in the string s using the counter class. This involves iterating through the string once, giving us an O(n) operation where n is the length of the string. Next, we calculate the odd frequencies by using the values method of the counter, which retrieves the character frequencies. Since values operates in O(m), where m is the number of distinct characters, and m is at most 26 for lowercase English letters, this step is effectively O(1). We then iterate over these frequencies to determine if they are odd, which is also O(m), or effectively O(1). Finally, the comparison odd underscore count equals k is a simple O(1) operation. Each of these steps contributes to the overall time complexity, but as we'll see, only the first step significantly impacts the total runtime. When we combine these steps, the dominant operation is the O(n) iteration required to count character frequencies. Therefore, the overall time complexity of the canConstruct function is O(n). Now, if we look at space complexity, the counter object is used to store the frequency of each distinct character. In the worst-case scenario, where all lowercase English letters are present, this requires O(26), which simplifies to O(1) space. Additionally, intermediate variables like odd underscore count and the result of char underscore count dot values only consume constant space, or O(1). Finally, as the input string s remains unmodified, no extra space is needed for the input itself beyond what is already provided. These factors lead to an overall space complexity of O(1), making the solution both time-efficient and space-efficient. To better understand the efficiency of the current approach, let's compare it to a naive brute force method. In a brute force approach, we would attempt to partition the string s into k substrings and then check if each substring is a palindrome. This would involve generating all possible subsets of the string, leading to a time complexity of O(n*(2 to the power of n). Such an exponential growth is computationally infeasible for larger strings. In contrast, the optimized solution focuses on the necessary condition of counting characters with odd frequencies, reducing the problem to an O(n) operation. This optimization not only makes the solution scalable but also minimizes space usage to O(1), by avoiding the use of additional data structures beyond the counter object. As a result, the current approach is both efficient and well-suited for this problem. Breaking down the time complexity further, we can analyze the best, average, and worst-case scenarios. In the best case, if k is greater than the length of the string s, we can immediately return false with an O(1) operation, as it is impossible to construct k palindrome strings. For the average and worst cases, the function needs to count character frequencies in O(n), and check odd frequencies in O(1), resulting in a consistent worst-case time complexity of O(n). From a mathematical perspective, the big O notation reflects the dominant term as the input size n increases. In this problem, the O, n, character frequency count outweighs all other operations. Additionally, the space usage remains constant at O, 1. This demonstrates that the solution is not only optimal in terms of time but also efficient in its use of space, adhering to the problem's constraints. When working on this problem, there are a few common mistakes to watch out for. First, ignoring the odd frequency constraint is a frequent oversight. Remember that for a string to form a palindrome, most characters must have even frequencies, with at most one character allowed to have an odd frequency for the center. If the number of odd frequency characters exceeds k, it's simply not possible to form k palindromes. Another mistake is overcomplicating the problem by trying to explicitly construct the palindromes. The problem only asks whether constructing k palindromes is feasible, it doesn't require actually building them. Instead, focus on counting character frequencies and analyzing the constraints efficiently. Finally, not handling edge cases can lead to incorrect results. For example, if k is greater than the length of the string, it's impossible to form k palindromes since there aren't enough characters. Similarly, if k is 0, no palindromes can be formed regardless of the string's content. Keeping these points in mind can help avoid some of the most common pitfalls. Another mistake to be aware of is misinterpreting the problem requirements. Some may assume that all k palindromes need to be of equal length, but that's not the case. The problem allows palindromes of varying lengths as long as you can form exactly k of them. This flexibility can simplify your approach. Additionally, inefficient frequency counting is a common issue. Some solutions use nested loops or redundant operations, which can unnecessarily increase complexity. Instead, you can calculate character frequencies in a single pass using a hash map or an array of size 26 for lowercase letters, achieving an O, n, time complexity. This approach is both simple and efficient, and it ensures your solution remains performant even for larger strings. From an interview perspective, there are some key insights to highlight. The core idea is understanding the relationship between odd frequency characters and the number of palindromes. A palindrome can incorporate one odd frequency character at its center, which means the total number of odd frequency characters determines whether forming k palindromes is feasible. This is a recurring theme in string manipulation problems, so recognizing this pattern can help you in similar challenges. Efficiently analyzing character frequencies using hash maps or arrays is a critical skill here. Time complexity is another point to emphasize. Counting frequencies takes O, n, while summing up odd counts is O, 1, for a fixed alphabet size, making the solution highly efficient. Be prepared to discuss edge cases, such as when k equals the length of the string, meaning each character forms its own palindrome, or when k is 1, meaning the entire string must be a single palindrome. This problem is closely related to a few others that you might encounter on LeetCode. For example, LeetCode 266, palindrome permutation, uses similar frequency-based logic to determine if a string can form a palindrome. LeetCode 131, palindrome partitioning, requires breaking a string into substrings where each substring is a palindrome. LeetCode 409, longest palindrome, focuses on constructing the longest possible palindrome using character frequencies. Lastly, LeetCode 5, longest palindromic substring, is about identifying and analyzing palindromic patterns within a string. Studying these problems can provide additional perspectives on how frequency analysis and palindrome construction are applied in different contexts. There are also alternative approaches to solving this problem. One option is a greedy approach, where you construct palindromes iteratively. Start by distributing odd frequency characters first, since they must occupy the center of a palindrome, and then fill in the rest with even frequency characters. While this approach may help you visualize the solution, it often results in a more complex implementation. Another option is a set-based approach, where you use a set to track unmatched characters. For each character in the string, you add it to the set if it's not already present or remove it if it is. The size of the set at the end represents the count of odd frequency characters. This method simplifies the code and provides an intuitive way to think about odd counts, but you'll need to explain why the set size is directly tied to the problem constraints. Both approaches offer valuable insights and can deepen your understanding of the problem structure. Great work! To wrap up, we reviewed the solution to LeetCode problem number 1400 and highlighted the key concepts involved in constructing palindrome strings. This problem showcases the importance of analyzing string properties and applying efficient algorithms. Remember to keep practicing similar problems to strengthen your problem-solving skills. Thank you for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!